Today we're going to talk about limit switches. A limit switch is very simply either a mechanical switch or a magnetic switch or an inductance switch which can sense position. Now in my last video I've got a magnet sensor back here that this thing sweeps across. There's one in the back over here, and you can see the wires right here. There's a sensor in here, and this is a magnet. When it comes up it'll sense it. Now some people say, why do you have magnetic switches? Why even bother? Because I can start my thing up, move it around, and set 0. Well, here's a perfect example. I've got these little boxes I had to do, and I designed this little unit to where I could snap them in, and I know that this corner should be the 0 point, and then it will cut my shapes perfectly. Alright? And in the machine I ended up having this little dimple from probably when we built it or I was first getting used to the machine, and it made a little dink in there. Well, since then I've been using that dink as a way of testing my accuracy. Now I could sit there with this thing and I could move it around and place it in there and reference it and then go off the distance and whatever. But I want to show you, you can see I do not have Linux CNC running, and I'll show you how limit switches and how homing switches are really useful. I can start this machine up, it comes up, turn it on, and tell it to home all. It's going to detect. Now it's going to do the X, and then it'll go back and it'll do the Y. Now, every time I home this thing, it's going to end up exactly right here. And to show you that, I've written a program because I measured what the distance was from there to here and set that as 0, and then I know what the distance is from there to there, and I can reliably go back to this point. Watch. I'll come in here and load this file. Alright, and when I run it, it's going to come down to here. And you see it's exactly on that point. I can get that same kind of accuracy every single time. And if I were to load the box routine and have it cut the notches in this box, I know that this box would come out exactly the way it's supposed to be every time. And to me that's very important. So let's talk about homing switches. This is a typical contact switch. It's only got 2 wires. One is ground, the other one goes to your sensor input. And the way it works is very simple. When something runs into this, it closes the contacts. When it closes the contacts, this becomes connected to this. So if this is ground and this is your input, it drops the input low. Now these switches are very handy. When something runs into them like that, it gives the contact, and you can get them in different types. This is probably more of what you're likely to see. And if you notice, this one has 3 contacts. Well, one of them is a common. In this case, this is the common right here. So that would connect to ground. And normally the ground is connected to this where it says normally closed. I don't know whether you can see that or not. And so it's normally connected to this, and it's not connected to this one. So you put your 2 wires from here to here, and then what happens is when something contacts this, it pushes on this little button inside and makes the contact. And a lot of people like to use this type of a switch. They'll mount it in, and when their carriage hits the end of the contact, it'll hit that and trigger the switch. Those are okay. You can also have it to where it swipes by and hits it. I've seen some with a little ball on there, a little wheel where it can contact it. But these are not my favorite kind of a switch. I like this, or this is one of the types that I like. This is a magnetic reed switch. And the way this thing works is inside there's 2 little fingers that react magnetically. Actually, let me show you a little diagram. So as you can see in this diagram, you've got 2 fingers. When the magnet comes close, the 2 fingers become attracted to each other and they'll contact. When the magnet gets pulled away, they open up. And you can get these with just a little glass shell, and it looks very similar to the diagram here, or you can get them like this. Okay, either way they react the same way. There's only 2 wires, and it doesn't matter which one goes to ground and which one goes to power, to your input rather. And yeah, they're real easy to connect, and they're very useful. Another type is the more complex sensor here, and these have 3 wires. There's a power supply, there's a ground, and then there's an output signal. And they usually have a little LED inside of here so that you can see that they've got power, and it'll come on dimly and it'll get bright. And these are available in 2 flavors. You can get an NPN, kind of like this, and you can get a PNP. And they look the same, right? Well, the NPN, the little blue line here, when you bring a magnetic source or a metallic source, depending on the sensor, and you bring it close, it will sense that, and that little blue lead will go to ground. In a PNP, that little lead is doing nothing, and when you bring the magnet close, it will go high. Now here's the interesting thing. If your little board, like mine, is set for 5 volts, and you're running this thing with 12 volts or so, and it goes high, it is going to way exceed the input and can cause it damage. And because of that, we use a little thing called an opto-isolator. And an opto-isolator is pretty simple once you understand how it works. So let me show you. So what you see here are the electronic symbols for a resistor, an infrared, or any kind of an LED actually, and a infrared phototransistor. Same one for a regular phototransistor, but these are the 3 main components that we're going to play with. And so let's go through how they work. Okay, so the first thing we'll do is we'll put in our input pin and our ground coming from our computer, alright? And we'll put some terminal blocks in so that we have a way of making some connections, and we'll put in a little block representing a 12-volt supply and its appropriate ground. So that now we have the basic players. Let's start wiring it up. Okay, so on the left hand side we've got our sensor. Now this is a PNP type sensor. So when it senses something, it's going to send the voltage out through the blue line going into our device. In this case it's going to be our LED. Now if you'll notice, the supply voltage is 12 volts. If we go and put 12 volts into an LED that's designed to run at 1.2 volts or so, we're going to blow it. We're going to smoke it. So we end up having to put a resistor in there. So how do we calculate the value of that resistor? Well, let's take a look. So let's see how we can do this. So here's our handy dandy calculator. Woohoo! Alright, so we take 12 volts and we subtract the operating voltage of the LED. 1.2 volts. That's from the spec sheet. Alright? That gives us 10.8 volts. Now, we take that and divide it by the current, which is 10 milliamps. 10 milliamps is the same thing as 0.010. Okay? 10 milliamps equals 1,080 ohms. Well, it doesn't have to be that critical. 1,000 ohms is fine. That's a 1K resistor. So we hook up a 1K resistor on that side. Okay, so now what we've got is we've got our 12 volts connected up to our sensor. When a metallic object comes near the sensor, the voltage is going to flow through that brown wire, through the sensor, and out through the blue wire. It's going to go across that resistor, which is going to limit the current, down through our LED, and it's going to make its path to ground. And when it does, this LED will illuminate. When it illuminates, it's going to shine on the sensor, shown in the purple right there. And that purple sensor, that infrared sensor, is going to conduct electricity, and the output pin is going to be pulled low, and therefore will sense the metallic object. Now I want you to notice that there is no electrical connection between that LED and that infrared sensor. They're totally isolated. The only thing that connects them is the beam of light. And so when we look at an optocoupler, which comes in a little package, they typically have 6,000 volts of separation. So it's a great way of protecting your circuitry. Well, that's what these are, these little 4N35s. They're a little plastic container, and they've got the LED and they've got the sensor in one convenient little package. See? So here's our circuit with the LED and the IR sensor on one side, and here's our 4N35, nice little plastic package. Okay, we go back to the circuit, and all we need to do is where we have our LED and our little IR sensor, pull them out and install the 4N35. We use pins 1 and 2, and we use pins 4 and 5. That's all there is to it. It gives us 6,000 volts of protection, and it'll definitely save your equipment if you have problems. The machine knows that this is its 0 point. It's real home. That's called a G53 home. That will never change because we've got our magnetic switches in there. Now, some people like to put a limit switch on the ends so that if it goes too far, it'll stop. It's unnecessary. It uses up extra inputs. If you know where this thing's home position is, you can tell how far you can go before you crash into something. And so what I'm going to do is I'm going to take this position and I'm going to go over into here and I'm going to do a touch off for each one of them and tell it that is 0. Go to the Y, tell it that is 0, and go to the Z and tell it that is 0. Now, yes, my home position will change, but we'll get into that in a little bit. So now I am set equal to where the magnetic sensors are. So here's the thing. I know that I can bring the Z down, and I can bring it down far enough that this metal piece will hit these plastic guides, which I don't want. So what I'm going to do is I'm going to see how far I can go. So I'll go down. And it looks like I can go to 85, neg 85, and not hit this. And I'm going to test that. I'll go here, and I'll do a G0 Z minus 85. And it gives me a little bit of space above here. So I'm going to write that down. Now I need to know how high up I can go. Because if I go too high up, this will crash into there, which would be bad. About Z6 is probably as high up as I want to take a chance on going. Maybe Z7. So let's say G0, Z7. Yeah, that's about as much as I want to do. So I'm going to go 7. So I know that my range for the Z is neg 85 to 7. Okay, cool. Next, what we're going to do is we're going to figure out what I can do for the Y and what I can do for the X. And I'll just figure that out off camera. No sense making you watch the whole thing. And then we'll get back to it. Okay, so let's start up the machine. And you can see that the box, the size of the world as the machine knows it, is way, way, way larger than reality. So we need to remedy that. We'll go into the step config. It's under CNC. Drop down to step config wizard. And we'll tell it start. We'll tell it to modify an existing file. Pull up our FrankenLab. And we'll get to the x-axis. There we go. So now you see it's set to minus 300 to 300. So now what we'll do is we'll type in the variables that we wrote down earlier that we actually measured. So minus 30 and 285. We'll go to the Y. We'll put in minus 285 there. And then we'll go over and we'll enter in our positive number. And then once we get done with that, we'll go to the Z and we'll do the same thing. We'll put in the numbers that we measured there. So we've got minus 75 on the low side, and on the upper side we've got 17. Alright, we'll go through the rest of the things, just keep going. Tell it yes, we're finished, and now it should update it. And if you'll notice, when this thing starts, notice the size of the box for the world. It's changed. It looks more realistic now. That's because we have fully defined our machine. Okay, so our machine is homed, and it has 000 here. So now the trick is, if I take this thing over and bring it to the left, am I going to be able to crash it into the plastic? And no, I cannot. Let's increase the speed. Try again. Won't let me do it. How about the Z-axis? If I take it down, can I crash it into the plastic? Nope. Well, the camera bumped into it. I didn't take that into account. But we're good. We're good. We're good. So that means I can run this thing around. Now what happens if I try to command it to do something? If I tell this thing G0, Y, 40, let's say, not a problem. If I tell this thing G0, Y minus 280, notice the little bumper stop here. And you notice it stopped. Now I can come in here and try to drive it further, and I've got a little bit more. I should have 5 more millimeters to go. And that's it. It will not let me drive it any further than that. Now what happens if I try to command it to do that? If I do a G0 Y minus 300, which would bring it past this thing here, and I tell it go, I don't know whether you can see it or not, but down here it's a warning, and it's just basically telling me, no, I'm not going to let you, because that would crash the machine. But if I try to drive it someplace that it's allowed to go, G0 Y minus 285, which is the maximum, it's very happy to run it right up to there. So you see, I don't need limit switches. And now you know how to set this thing up to where it's not going to crash into anything. And all it takes is the 3 basic homing switches for the Z, the X, and the Y. Now here's something else that you can do. We can command this thing to go back to home. G0, X0, Y0, Z0. Now, that's where it's going to end up when it homes. Now, if I were to tell it to home right now, okay, it's going to find that magnet right here, and it's going to just barely go up and then bump into it. The x-axis, same thing. Ideally, we want to be off of the magnets the same way each time. So if I were to tell this thing G0, Z minus, we'll say 10, Y minus 20, and X 20, that would drive it over to a point here, which would be a great starting point for the zeroing sequence. Well, here's a trick. You can do a G30.1. That stores one location. It's a special location. So now I can be running this machine around all day long. And to go back to that position, all I have to do is execute a G30. It'll take me to that position. Now what I can do is I can shut the machine down, go away, come back the next day, start up the controller, and guess what? When I hit home, everything's going to go the right way, and it's going to end up exactly the same. So that's all the tips I have for today. We'll get some more later, and I hope you enjoyed it. You see what I go through? I've got my backdrop set up and my lights, and I've got at least 2 or 3 different cameras running. And why do I do all this? I do it for you. If you like the videos, leave me a comment down there. Let me know about it. If there's something you want to know, let me know. I'm here for you, okay? And thanks for watching. Yeah, I know, it's scruffy. It's a Saturday and I didn't feel like shaving, so